Welcome you all to the video on part of Unit 5, which is the cyclic codes. So these cyclic codes are another way of representing the linear block codes, or we can call them as the subclass of linear block codes. So how do we differentiate the normal linear block code with the cyclic code is they have two advantages over linear block code. One is the advantage over linear block code the cyclic codes has the encoding and syndrome calculating circuits are easier to implement. The syndrome calculation circuit are easy to realize or implement with simple shift registers and with feedback connections. There's a simple shift registers with feedback connections where the feedback information will be obtained by making use of some basic gates. So what we will do is this is again the cyclic codes are the codes or the coded information obtained for a block of information code, but this particular type of code will help us in achieving the encoding and the syndrome calculation circuit to be much easier during the implementation in a practical scenario. So how does it simplify the implementation is, so in the linear block codes we saw that there were multiple different basic gates and shift registers that were required when it came to the syndrome calculation circuit or the encoding circuit. The number of gates that were involved were too many, but here with a single shift register and only few basic gates with a feedback connection, we will be able to achieve easily implementable encoding and syndrome calculation circuit. So this is the first advantage. And the second advantage that we obtain is the cyclic codes have a what is known as mathematical structure. So what is this mathematical structure when it comes to the arrangement of the redundancy and the information? We can easily identify the position, and then we can also obtain, if we know one of the code words, we can obtain all other code words that belong to the given code set without knowing even the parity check matrix. So these are some of the very unique characteristics which are based on their mathematical structure, and also depending on their implementation they play a very significant role in practical systems. So now we are going to look at how these we will see in this particular part how these cyclic codes are realized and how they are generated, how we are going to use them for error for transmission as well as error detection and correction. So before we move ahead, we will have to know the definition why the name cyclic code is coming. So first we will consider, as I said, the cyclic code is a form of linear block code. Therefore the cyclic codes are also identified as n comma k linear block code or n comma k linear cyclic code. So an n comma k linear block code, so since I say this as a subclass, an n comma k linear block code is said to be a cyclic code. We can call a n comma k linear block code as a cyclic code if every cyclic shift of the code is also a code vector. That is the uniqueness. That's the name cyclic codes. It has been provided. So what does that mean? If I have assume that I have a code vector called 101101 for an example. Assume that this is a 6-bit code word. If at all if I do a cyclic shift, that means this bit is being shifted to the beginning of the code word. So this becomes, this transformed version will be, I'll name this as v dash, or let me name this as v1 because it is being shifted by one position. In that case your code word will be 110110. So even if after cyclic shift the so obtained 6-bit n-bit code word, if at all if this is also a code word, if this is also a code word for one of the message, for one of the message combination, then we call this type of this should hold good for any number of cyclic shift. If that is so, then we call such a code as the cyclic codes. So basically, let me consider one particular example over here. Let the c1, the code word c1 be equal to 0 1 1 1 0 0 1. This is a 7-bit code word of be a code vector. This be a code vector of code set C. Then assume that I have C2, which is a cyclic shifted version of the C1, where the last bit has been shifted to the beginning. That is 1 0 1 1 followed by 00. If this C2, it is such that, so if I have moved, since I have moved one bit of C1 to the beginning, if C2 also belong to the code set C, then we call such a code as cyclic code. If again, let us suppose, and there is another code word called C3, where the last bit of C2 has been shifted to the beginning, then in that case it will be 1 0 0 1 1 0. If this one more shift, it is 00 10 1 1. If these two also belong to the code set C, then we call such a code word set as the cyclic codes. So let me consider a very generalized expression over here. Assume that we have a code vector called as v0, v, where it consists of n number of bits, that is v0 v1 v2 so on up to v of n minus 1. So there are totally n bits in this code vector. If at all if I apply a cyclic code, that is assume that this is a representation of the code vector v, which is shifted by cyclically shifted by one position. So this is the cyclic shift number of cyclic shift that is done on the vector v. So if I do the first cyclic shift, that means the v of n minus 1 will come to the beginning, followed by rest of the bits, that is v0 v1 v2 so on. So the last bit would be v of n minus 2 in this case. So this also becomes one of the code word. Let me do the second cyclic shift, where v of n minus 2 will come to the beginning and rest all gets shifted to the right. So this new code word vector would be vn minus 2 vn minus 1 v0 v1 v2 so on v of n minus 3. If I repeat for I positions, I number of positions, then I can write in general v of n minus I, v of n minus I plus 1, v naught. So this repeats somewhere in between. I'm going to get v naught. This is v naught, v1, v2 so on. So the last one would be v of n minus I minus 1. So this is the ith cyclic shift that is obtained. If we are shifting v vector cyclically and successively, If all these are also vectors, then we call such the such of the code words a code word set as this belong to a code set C, and this code set C will be called as cyclic code set or cyclic code vectors. Okay, so this is a generalized expression for an n bit cyclic coded vector, where the cyclic shift operated on one of the code word will lead to another code word. Now, since if I know one of the code words, then the rest of the cyclic shifts will give me all other possible code word vectors in a given code set. I can represent, we will make it easier for the representation of the all code words by writing the v vector in terms of a polynomial in x. So how to write the code vector in terms of its polynomial is, we are going to assign the positions for each one of the bit position. Starting from the extreme left will be assigned with, assume that I'll consider a previous example itself. Assume that I have a code v with coefficients v0, v1, v2, so on up to v of n minus 1. Now this code vector can be represented as a polynomial in x. So how to do this? We treat this as LSB and we treat this as MSB, and with respect to the position, this corresponds to x raised to 0, this corresponds to x raised to 1, x square, so on up to x raised to n minus 1. So therefore this is a polynomial in with the maximum degree of x as n minus 1. So I can write this as v0 into x raised to 0 plus v1 into x power 1 plus v2 into x power 2, so on v of n minus 1 into x raised to n minus 1. So therefore this can be written as, since x power 0 is 1, v0 plus v1x plus v2x square plus so on v of n minus 1 x raised to n minus 1. So this is the polynomial representation of a code vector. Similarly, the cyclically shifted code vector can be written as v of n minus 1 plus v0 into x. Now this coefficient will come to the beginning, therefore it will be corresponding to the position x raised to 0. Therefore we have vn minus 1 plus v0 of v0 into x plus v1 into x square plus v2 into x cube, so on. The last one would be vn minus 2 into x power n minus 1. Similarly, the second cyclic shifted version would be vn minus 2 plus vn minus 1 into x plus vn minus v0 is x square plus v1 is x cube, so on. The last one would be vn minus 3 x raised to n minus 1. So if we apply the same analogy to the ith cyclic shifted successive ith cyclic shifts, then we obtain vn minus I plus vn minus I plus 1 into x plus vn minus I plus 2 into x square, so on. And the last one would be vn minus I minus 1 into x raised to n minus 1. So this is the representation of the all the code words, all the possible cyclic code words in terms of their polynomial representation. So why do we require this polynomial representation is, each one of the polynomial or the operation of obtaining a code word or calculation of the syndrome will be calculated in this transform domain or in the x by making use of polynomials, because it is easier to implement mathematically, and then we can easily understand the concept of coding in case of cyclic codes. So to understand this multiplication or the polynomial algebra that is associated with the cyclic codes, we need to look at some of the modulo 2 algebra operations, so that we can get accustomed with the some of the operations done on these polynomials in X. So now we will look at modulo 2 algebra. So we know that in algebra we have basic mathematical operations, like we are going to look at addition, we will be looking at subtraction in modulo 2 version, multiplication and division. So these four operations, basic operations, we will see here. So first and the foremost thing is the modulo 2 addition. So in the modulo 2 addition of the polynomials, it is simple. Assume that I have x plus x as one of the equation, or some I want to evaluate this value of x plus x in terms of modulo 2 arithmetic. In that case, it is simple. Consider x as a common 1 plus 1. So this 1 plus 1 in modulo 2 algebra or modulo 2 arithmetic, please remember this operations, that is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. And then if it comes to multiplication, similarly 0 dot 0 is 0, 0 dot 1 is 0, 1 dot 0 is 0, and 1 dot 1 is 1. So keeping this in mind, we know that 1 plus 1 is 0, therefore this leads to x multiplied by 0, which is nothing but a 0. So addition of two similar terms will lead to 0. Similarly, x square plus x square is equal to x square in common 1 plus 1. So therefore this is x square multiplied by 0. This is gives us 0 as the result. Now subtraction in modulo 2 arithmetic is same as addition. So there is no difference between multiplication and addition and subtraction in case of modulo 2 algebra. So it is same as addition. So there is no difference in modulo 2 subtraction. Coming to the multiplication operation, this is very important, because most of the times whenever we have to find out the code vector for a message, we are going to write both the message sequence as well as the generator in terms of the polynomials. So you will have to multiply. Therefore this knowing the process of multiplication is important. So if I consider a polynomial as x and another polynomial as x, so the resultant would be x square. If at all I have a polynomial called x square multiplied with x, the resultant would be x cube. As simple as that. Let me consider a very simple example over here, where I have a polynomial in x called f1 given by x plus 1. I have another polynomial f2 in x with the polynomial as x cube plus x plus 1. So what I need to do is to do the multiplication operation on the two given polynomials. So how to do this? Let me consider x plus 1 multiplied by x cube plus x plus 1. So this multiplication operation will involve two arithmetic operation. One is just simple multiplication of two elements. After multiplying, we'll have to add similar terms. So multiplication and addition will take place in this particular operation. So how to do this? Let me multiply first all the elements in the second function with respect to x. That means I'm going to get x raised to 4 plus x square. See, I'm leaving a position over here so that there is a space for x cube, x square plus x. So this is the polynomial that I get by multiplying it with x. Then I have to multiply all the terms with respect to 1. So how do? I'll consider x cube. So this is an addition. So continuation, I'm writing it in the other line so that we can understand what are the resultants. I can easily add up all the terms. Then the next term is x plus 1. So this is how I am going to get. Let me resolve this. So to resolve this, please look at the common terms over here. So for x power 4, there is no another x power 4. So it is like 0 into x power 4 over here. This is 0 into x cube. Here it is 1 into x cube. It is 0 into x square. Here it is 1 into x square. So here there is a 1. Here there is a 1. So it is 0 into 1. So please remember this. So whenever I write this in terms of x raised to 4, I have 1 plus 0. If you take x cube in common, I have 0 plus 1. If you take x square, I have 1 plus 0. If you take x in common, I have 1 plus 1. If you take 1 in common, I have 0 plus 1. As simple as that. So the resultant of this multiplication, so you can see over here the coefficients are adding to 1, 1, 1. Here it is 0 and here it is 1. So therefore, that means I can write simply this expression that I am going to obtain as wherever the coefficients have the similar kind of, wherever the variable in x has a similar coefficient, that is either a 0 or a 1, they cancel out each other, they lead to 0, and whatever the coefficients, if they are different, then they are going to retain as it is, that is x raised to 4 plus x cube. Actually this wasn't there, I have written this as 0 into x power 4, so this wasn't there. So you can just add them up. Anything added with 0 means it will retain the same thing. Therefore x power 4 x cube plus x square plus this one will not be there, we'll have a 1 over here. So this is the resultant of your multiplication of two polynomials in x. This is about the multiplication. Now we will see the division operation which is done on polynomial in x, which is again where the coefficients of the polynomial are either a 0 or a 1. So keeping that in mind, now we are going to look at the binary division or the modulo 2 division operation. So modulo 2 division, again I need two functions. Let me consider function f2 with the polynomial in x as x raised to 6 plus x power 5 plus x square. I need to divide this by f1 of x, which is equal to x cube plus x plus 1. So how to do this division is, again you have to write the MSB part of each one of these polynomials to the extreme left, that is highest power should come to the extreme left, that is x cube plus x plus 1. Similarly in f2 also you have to write x raised to 6 x raised to 5 plus x square. So now the division needs to be done. To do the division part, we will see now. So in order to division, in order for the division to occur, we have to make the powers of x to be the same. So whatever the resultant that I get over here, I need to have the common power for them to get divided. So the term that is required here is x cube, because x cube into x cube will lead to x raised to 6 because the powers get added. So therefore this is x power 6. X cube into x is x power 4. X cube into 1 is x cube. So now you can see there is only one term. So you are supposed to subtract here. The subtraction operation is similar to addition. Therefore this similar terms will vanish. Only the dissimilar terms will exist. That is x raised to 5, x power 4 plus x power 3 plus x square will remain. Now again I need to equate it. This power of x is greater than power of 3, power in the divisor. So therefore this polynomial will divide further. Now I'll make it equal by multiplying it with x square. Now if you multiply x square with the divisor, you're going to get x power 5 plus x cube plus x square. So observe carefully. You're going to get x power 5, x cube and x square. So now all the similar terms will vanish, only the dissimilar term will remain. Now again the power of x is 4, which is greater than the power of x, which is 3 in this divisor. So I multiply it with just x. So you're going to get x power 4 plus x square plus x. So leftover is, so again similar terms will cancel. Leftover term is x square plus x. Now the power of x in the remainder is lesser than the power of x in the divisor. Now the division ceases. So therefore the resultant that I obtain over here is called as remainder polynomial. Remainder polynomial, and it is denoted as r of x, capital R of x, and this is known as q of x, which is the quotient polynomial. This we call it as quotient polynomial, and then this r of x is called as a remainder polynomial. These four are the modulo 2 algebra that are required for the cyclic course. Along with this, we are going to define what is known as the Galois field. What is this Galois field? A field is nothing but, a field is defined as a finite set of elements. Let us suppose I have a set called as X, which is consisting of a limited number of elements in it, that is finite set of elements, such that this all the elements in this particular set are going to satisfy, are eligible, are satisfying the associative property, commutative property, okay, associative, commutative property, distributive law, and it has to has a unit element and an inverse element. So what does that mean? If you do any operation on this particular field, all that operation should satisfy this associative property, commutative property, distributive law, unit element and an inverse element. So the operations that we do on this particular set, we denote it with operations like, assume that for the Galois field we normally go with multiplication and addition. So let me consider a very simple example over here. A Galois field, let me consider this set will consist of just 0 and 1. So if we consider multiplication and division, multiplication and addition done on only these two elements, as I wrote, it is 0 into 0. So if you take an element from the same set, if you take another element from the same set, if the multiplication operation is leading to an element belonging to the same field, then we call such thing as Galois field. Okay, so if we consider 0 and a 1, again it is 0 which belongs to the same set. 1 multiplied by 0, again a 0 which belongs to the same set. 1 multiplied by 1 is again 1 which belongs to the same set. If you do similarly the addition operation, 0 and 0 plus 0 is 0 which is belonging to the same set. 0 plus 1 is 1, 1 plus 1 is 0, sorry, 1 plus 1 is 0, 1 plus 0 is 1. So all these elements, the resultant elements, whether this or this, are belonging to the same set. So therefore such a set is said to be, or we call them as a field. And since why we call it as a Galois field is because this involves only two fields, and this is also called as binary field, and this was figured out by a person called as Galois. Therefore in his name this has been, the binary field is named as Galois field. This is also known as binary field. So depending on the number of elements that I have in this set, the name can be given. Actually, the number of sets, number of elements in a given set would be normally, in terms of Galois field, we always define it as g of f, and this is written as the prime number. We consider prime number of elements in a given set, which can be extended to q number of extensions. So what does that mean? Let me consider a Galois field. Now this is a Galois field of 2, where I have only 2 elements, which is either a 0 or a 1, which is satisfying all the criteria of a field. So this is gf of 2. There is, I can also write an extended field called gf of 2 raised to m. So what is this gf of 2 raised to m? So we know that we have been addressing all our bit stream, which is somewhat like this. I assume it is 1 1 0 1 1 1. So this is nothing but up, I can represent this in polynomial. I can represent it in what is known as the simple time representation is 1 1 0 1 1 1. In polynomial, I can write this as 1 plus x cube plus x raised to 4 plus x raised to 5. So we know that there are totally 6 bits which can be represented in polynomial like this, or in time domain like this, or I can also write this in an n dimensional vector space. That means 1 into 1 followed by zeros, that is 6 dimensional vector, plus 0, second bit is 1 multiplied by 0 1 0 0 0 0 plus, plus means in that particular position you are going to have, so it is 0 into 0 0 1 0 0 0 plus 1 into 0 0 0 1 0 0, then 1 into 0 0 0 0 1 0, last one 1 into 0 0 0 0 0 1. So I can represent every code vector in terms of m number of unique, 2 power m number of unique such code vectors. So depending on how many ever numbers, since I can represent any given code vector in terms of their equivalent n dimensional vector, since it is possible, this m represents the possible number of, how many bit sequence I have, and this gives me to what dimension I can extend it to. So that means if I have or this represents how many code vectors can be represented, and m represents the dimension. So assume that I have Galois field of 2 power 4. In that case, using the 4 dimensions, I can represent any of 16 combinations. So what does that mean? If I have a 4 dimensional unique vectors, that is 1 0 0 0, the other one is 0 1 0 0, the third one is 0 0 1 0, the last one is 0 0 0 1. If I have these 4 unique code words, or if I have these unique what are known as vectors, unit vectors, then I can represent any of the 16 combinations by making the linear combinations of these 4 vectors. So therefore we call this as extended Galois field, or the extended binary field, which is 2 power 4. So depending on what we have in the Galois field in the power of 2, so many number of bits are used in representing the code word, and that is the code vectors, which is something or sequence like this, and 2 power m will represent the number of possible combinations or the valid code words in that particular Galois field. So why we require this is, whenever we are generating a cyclic code, all the cyclic codes or the polynomials will be obtained from the Galois field only, whether it is from the gf of 2 or gf of 2 raised to m. So depending on this m value only, we are going to pick the coefficients of the code word, or the generator polynomial will be generated from the Galois field or the extended Galois field. So once we know about extended Galois field, we have to define about what is known as primitive polynomial. So this is a kind of a unique polynomial that we define, where the coefficients of the polynomial are obtained from gf of 2. The algebra can be derived from the polynomial of degree m, which is where the coefficients are obtained or derived from the Galois field of 2 power m. Assume that I have a polynomial of degree m, that is polynomial in x with degree as m. So if I have a polynomial of in x with a degree m, if at all there exists a value called as, in place of x, if I replace it with an element called as alpha, and this leads to a value 0, then that means all these alphas should be again from the gf of 2. That means the coefficient should be from the gf of 2. Therefore the possible alpha values that it can take is from the gf of 2, which is either a 0 or 1. When you substitute a 0 or 1 in place of x, if the resultant is 0, then alpha is known as the primitive element. That means the root of that particular polynomial, whether it is 0 or 1, that is called as a primitive element. If at all I have a polynomial in x which is irreducible, that means I do not this particular polynomial is not having any factors. Irreducible means p of x does not possess any factors. That means there are no roots for this particular polynomial. Then such a polynomial is called as p of x, which is irreducible, is known as primitive polynomial. This is a very important concept that we require, because if at all, whenever we are generating a cyclic code using a generator polynomial, we always talk in terms of polynomial. So generator polynomial usually is a primitive polynomial. So we will see a simple example what is meant by primitive polynomial. Let us consider a function or a polynomial in x, f of x, which is x raised to 4 plus x cube plus x square plus 1. So what I did say is, since this is a polynomial defined on gf of 2, the two possible values that x can take is from the given set of from the Galois field 2, which is either a 0 or a 1. Now let us substitute 0 and a 1 in the above case and check if this leads to a value equal to 1. So for the case when I substitute x as 0, I get 0 plus 0 plus 0 plus 1. So this leads to an answer called as 1. Let me consider the x value being substituted as 1. That means x is equal to 1 here. And this was x is equal to 0. For x is equal to 1, I have 1 plus 1 plus 1 plus 1. Here you can see 1 plus 1 is 0. 0 plus 0 is 0. So here you are getting a case where one of the resultant is 0. So therefore the primitive element for the above polynomial is alpha, which is with a value equal to 1. So therefore this polynomial is not primitive. Now let me consider another example here. Let me consider another example here. where this happens to be the case where I have 1 plus x cube. I consider another function called as 1 plus x cube. In that case, put x is equal to 0. So f of 0 would be 1 plus 0, which leads to a value equal to 1. Now put x is equal to 1. This becomes f of x, f of 1, which is 1 plus 1. In that case, do the grouping. 1 plus 1 is 0, 0 plus 1 is equal to 1. So either when you apply 0 or a 1, in both the scenarios you are getting the function value as equal to 1. So therefore this particular polynomial is called as a primitive polynomial. There is no root for this particular polynomial, so none of the elements are leading to a value equal to 0. Such a polynomial is known as primitive polynomial. Only such primitive polynomials can be used for the generation of the cyclic code. So in our next video we shall see how to generate the cyclic code words using the generator polynomial. Thank you.